Okay, I think we can go ahead and get started. Welcome, everyone. It's my pleasure to introduce our colloquium speaker, Dr. Eva Schinnerer from MPIA. She's currently at Caltech visiting right now, so she's right in the neighborhood. Eva got her PhD from the Ludwig Maximilian University of Munich, while also working with Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics. She went on to Caltech as the Owens Valley Radio Observatory millimeter array postdoctoral scholar, and then on as the Jansky postdoctoral scholar at the NRAO. She joined MPIA as a staff scientist in 2004 and is an adjunct associated astronomer at NRAO. So we're going to hear today about star formation in nearby galaxies. Take it away.
Thank you. I'd like to thank you very much for inviting me and giving me the opportunity to present you the PHANGS project and what it entails, and also some highlights. So the idea of PHANGS to put into place was basically to understand the star formation process in nearby galaxies by using very high resolution observations of the different constituents. So like you can see from this galaxy, and the reason why we wanted to have a cloud scale view, which means about 100 parsec or better, is basically in order to understand which physical processes control the formation of stars by setting the initial conditions outside molecular clouds. And for that, the processes to consider are, of course, gravity, like what is pushing material around, but also even then smaller scale self-gravity, when you start to think of where the molecular cloud starts to collapse and starts to form indeed individual stars. That is the part I happily leave to my galactic colleagues to investigate more, talk about. The next step is turbulence, and there are basically two parts of turbulence you can consider. The one is small scale, that is basically what is injected into the interstellar medium when our stars are forming in the form of, we have winds from protostars by doing their formation. You can think about supernova explosions, but also then on a large scale, you know that galaxies have galactic structures like spiral arms or bars, and these of course induce also large-scale motions in the disks, and they also could have an impact on the star formation process. And the last thing to consider is, of course, then radiations, of impact of radiation onto the interstellar medium, and also its impact in the formation process of stars. So just to tell you that basically this provides you, this is the same galaxy, just viewed in different tracers, and it's very clear that having those at very high resolution is important and critical to understand what individual star forming regions, you see them in the bottom, H2 regions in red, showing up compared to clusters in the bottom right. There you have the little things, and then how that compares to the distribution of the material out of which these stars are born. So basically, understanding the star formation process is talking about looking at the baryon life cycle within a galaxy. So what you see here basically is a small part out of a galaxy where you basically see the different stages of the star formation process that you're trying to sample and to understand. So let's start off with diffuse atomic gas, which kind of is the raw material. If it becomes more dense, the gas becomes, the neutral cold gas becomes molecular. The molecular gas can start to become self-gravitating, collapse, form stars, star clusters. Those clusters during their formation are starting to reprocess their surrounding birth cloud, and you're getting H2 regions. You have supernova impacting its stellar ejector. Most of this will act to basically dissociate the molecular gas of birth cloud and have an impact. And once the gas, ionized gas, has much time to cool, it might become atomic again, and the cycling matter cycle starts again. So in order to observe this, you basically need atomic gas, molecular, tracer of a molecular gas, so the CO line here. Stars, you want to sample the photospheres, you do that from the UV to the near infrared, and then to study the impact, you can think about ionized gas lines or a radio continuum. And if you look here and you probably spotted all the little icons. It tells you that you basically need a multi-wavelength approach to sample this cycle completely. So for the cause of this talk, I'll be focusing more on the right-hand side, and more general questions to address are where, when, and how do stars form? Do they form everywhere in a galaxy? Is it always the same process? How efficient is star formation? Does it depend on where in the galaxy you're located? Or is it the same everywhere? How long does it take to form stars? Is this a fast process that happens within a few million years? Or if you consider the full aspect here from molecular reservoir to star, does that take very long? How long can it proceed within a cloud or a star formation unit of about 100 parsec or so? And what basically shuts off star formation? And I'm not sure I'll give you answers to all of these, but just to give you some ideas what we have learned over the past years. So where and how do you study it? So we know the majority of stars forming in main sequence star-forming galaxies, and basically ALMA has revolutionized our way how we can address it. So this is just one picture. ALMA is a sub-millimeter interferometer sitting at 5,000 feet in southern Chile, consisting of 64 antennas with 3 components. It's the main array that offers you highest resolution, highest sensitivity, but also then a component that's the Atacama compact array that provides you information on the more diffuse distribution and the larger scale emission. And you need to combine those to achieve very good imaging. So why is it the ALMA resolution? So what you see here is now about 10 years old data on the right-hand side. This to date was at that time the best map of a molecular gas in a normal star-forming disk similar to our Milky Way that could be achieved. It took 170 hours, so it was a large program. Very clearly, it was not very clear. This would not be possible to do it for a large sample where you could start doing start to do statistics and see if there are variations. The thing, it already showed the promise that ALMA will have. You see the spiral arms are resolved. You have structures like gas bursts sticking out. There's definitely emission between the spiral arms and what goes on. So ALMA now allows you to take maps like that within about 2 hours with the main array. And I said, when you want to study the star formation process, you would like to sample galaxies that are sitting on the main sequence of star-forming galaxies that's in the plane of global star formation rate versus local stellar mass. There's this very tight relation between 2 galaxies. And the surprising thing is that if you look at the star formation rate density per stellar mass per volume, you basically see that the galaxies that contribute most to the star formation rate density are galaxies like our Milky Way. And this is independent if you look at the more local sample or if you go out to high redshift like redshift 2. So which also tells you that studying characteristic star-forming galaxies locally, you potentially could learn also some insights for going out to higher redshifts. So with that basically in mind, we started the physics at high angular resolution in nearby galaxy projects now about 6 years ago. The aim was to understand the interplay between the small scale physics that we can probe at 100 parsec resolution, or so with that of with galactic structure and also galaxy evolution. So the galaxy evolution aspect basically drove us to pick the sample to lie on the main sequence and to sample it fairly well, which it kind of does, despite the fact that we restricted our distance cut to about 70 megaparsec, so that the seeing of 1 arcsecond still gives us decent resolution. We didn't want to have the galaxies to be edge-on because we wanted to understand relations within the disks, and then the requirement was that the sample is ALMA visible. So this is currently the team. It has grown significantly over the last few years, and you might recognize Guillermo, who was together with Eric, Adam, and Eric Roslowski, one of the co-people with whom we basically set up this project to get it started. And this was the picture of our last team meeting a few years ago in Madrid. So how do we sample the baryon life cycle or star formation process? So what we do is basically we take ALMA observations to probe about 100,000 molecular clouds. In order to do so, this is a sample of 90 galaxies. The next step is basically going after the embedded star formation and also getting the dust. So this is very new, that JWST is basically allowing to do us since last July. This is combined with HST imaging, where we get access to very young stellar clusters and stellar associations. And lastly, we use optical IFU provided with the MUSE instrument on the VLT to get access to the H2 regions, their properties, but also to the underlying stellar population physics. So you see our base sample is ALMA with 90 galaxies. The second largest cover has about half of them are covered by JWST and MUSE, by HST and MUSE, and JWST are the one where we have only a quarter. So basically for 19 galaxies, they have all data from, or will have data from all these major instruments. So these are the 4 large or treasury programs. And I just want to show you a little bit the science. So these are the 90 galaxies. They are sorted. So you see the molecular gas distribution at about 100 parsec resolution across the inner star forming disk. So this doesn't go out to the full outer optical disk, but the part that is rich in star formation, because we wanted to be efficient with the star formation time. So this image, basically, you just to see the variety. So these are grand-design spirals, multi-arm spirals that show up in molecular gas. And here it's just some more diffuse distributions with not much structure in molecular gas. So this already tells you that somehow the molecular gas distribution knows about what kind of galaxy it's sitting in or the underlying gravitational potential. These people have worked very hard over 5 years to get the data products into shape and public and usable for doing science. The next set is JWST. So these were the 4 galaxies observed by JWST. These are their MIRI composites. I assume you probably have all seen the bottom image, which was the first galaxy observed and widely advertised. So just to give you an idea. In addition to the MIRI bands that are used in the mission, there's also some NIRCam observations, and the idea is basically to complement the HST imaging with more photospheric filters to probe the stars, to go after the PAHs, the polyaromatic hydrocarbonates. So it's the very smallest structures of the dust emission, and then also to have a handle on the hot dust, so the small, very small grains. That was the motivation to come up with this imaging survey.
Could you tell us how big the fields are that you have to cover?
Typically it's a few arc minutes. And yes, so I think typically our JWST images are 1 or 2 pointings. For MUSE, it's between 3 to 15. And ALMA, ALMA has a limit on the number of individual pointings you can do per field. That's 150. And we have between typically around 150 of these pointings, or 2 to 3 times that to cover the galaxies. So these are the people who have worked very hard about the summer and early fall to get the data into shape to enable a set of science exploitation of the data. Then the third aspect is HST, and these are some of the composites here to give you an idea. And how does PHANGS compare to GOLDS, which are basically sampling starburst galaxies? So you see it's sitting above the main sequence, and the laggers, who basically covers a very wide range in stellar mass and star formation rate. So you see that PHANGS HST basically sits in between these 2 samples, so filling out that you have a nicely filled main sequence or sampled. So these are the people who have worked the past 4 years to get HST imaging done, and particularly understanding the catalogs and producing catalogs and understanding how to estimate ages and masses of stellar clusters. So the last part is the Muse IFU. So these are composites by basically using these filters into the spectral cubes. And Muse, PHANGS Muse is basically, if you look at spatial resolution, it's very high. Of course, LVM will be much better. And the number of spatial resolution elements that are independent in the sense that they're independent by seeing, of course, you're sitting in galaxies and one pixel in a stellar disk next to the other is not physically independent, but it rivals the number of spectra that are in the first Sloan spectroscopic survey. So just to give you an idea how the processing and getting the information is quite demanding. So spatial resolution versus number of galaxies, with looking at the trend, you basically see LBM can only do a few galaxies, then PHANGS is in the regime that you expect basically by the number of targets you can get if you have to spend a lot of pointing. So the PHANGS pointings, the number of pointings we had 178 and we added probably another 10, 15 from the from the archive. So just to give you an idea on how much time that required. So this is then the information you can get. You can also just obtain the spectral line information. So what you see in blue here are planetary nebulae, and you see also in red more prominent the H2 regions. And also I should give credit to the people who have worked really hard to get the data in good shape, produce the catalogs, and I guess you recognize Guillermo here. So now moving on to basically some of the science questions. I'll start off with molecular gas. That's the phase out of which are stars born. So to understand here, I will use line width of the gas because we have a resolution of about 2 kilometers per second. We can perfectly resolve our line emission as a proxy for the turbulence, that internal turbulence or pressure. That is basically then telling you something about the kinetic energy. And similarly, the gas surface density is a proxy for the mass that's available and then the potential energy. So using the first initial set, Jai's son, back then at his PhD that he did with Adam Leroy at OSU, looked basically at the distribution of the gas surface density versus velocity dispersion. And he recognized that there was a very tight relation between these two parameters. And if you basically look at these lines, you see that this is the ratio between the kinetic to the to a potential energy. So very clearly the gas is kind of sitting in any energy equipartition, despite the fact the internal turbulence in the gas is very large, which is shown by the dotted lines. So this was using the initial first 12 galaxies plus archival data from the antennae and Andromeda and the Triangulum galaxy. And this basically comparing that to this internal pressure to looking at the pressure that is set by the weight of the gas in the stellar disk. So the hydrostatic pressure or the dynamic energy, that basically these two are very close. This was work already suggested 10 years ago, and these are just some references. So using the full sample, Jai in another work basically checked if indeed the pressure, the internal pressure of a gas and the external pressure, if they are agreeing. And what he found is that they do agree very well, but the red line basically tells you the 1-to-1. So there is an offset and the clouds seem to be overpressurized compared to what you expect. And in order to understand what could be causing that, he and his co-authors, they basically find that you need to account also the cloud self-gravity, so that the molecular material, you have to take that into account, and then basically you find that the cloud internal pressure knows about the ambient environment it's sitting in. So this is basically very important. So it tells you that a cloud, or what we call a molecular cloud, kind of knows where it's living in. And also you see that if you are in a higher density part, that is the self-gravity of a cloud that becomes more important to determine its factors. So what does that imply for these properties of the global galaxy properties? So are there any trends? So again, this is the global star formation rate versus stellar mass. And what you see here is the gas surface density. And you see that the gas surface density is always higher in the more massive galaxies, which is not totally surprising, because down here you're getting in the regime where the ISM is atomic dominated, and there's maybe a trend with star formation rate. The other thing that becomes more interesting if you look at the scales is that you basically see that galaxy disks, no matter where you're looking, are behaving very similar in their properties, but galaxy centers, in particular the centers of barred galaxies, appear to be more distinct, and I'll come to that later. And also there was always the question, is star formation happening the same in spiral arms or not? So based from the molecular gas properties, it seems that molecular gas is more dense in spiral arms compared to the interarm region. So basically, motivated by this, GI did a very comprehensive study and a systematic search. So he looked at different parameters for the molecular gas, mass, radius, surface density, versus metrics that cover the local environment versus the global environment. And what you see here is now the brighter the color, the stronger the correlation, if it is in red, or in blue if there's an anti-correlation. And the first thing that comes apparent is basically that there are more strong correlations with local matrices that are measured at about a kiloparsec resolution. And this leads to the conclusion that the local environment is more important in setting the small scale gas properties than the global environment of a galaxy. And a speculation basically is that the scatter one observes between galaxies to galaxies might be driven by the variation of the local environments different galaxies contain. So what will JWST bring to this? So what you see here is an HST image. Then you see basically HST and in red the dust distribution. So you can start to combine the absorption that you see of the cold neutral ISM with its emission. And you can start to trace out this dusty filamentary network. So this is a paper by Dave Filker. And one application, and I think potentially very interesting to theorists, is we potentially could start to understand which processes set the ISM structure. So this filamentary structure. And one way to look at it is a recent paper by Sharon Might, where she basically used the image you just saw before and tried to trace out these filaments, and then was asking what is the typical separation between these filaments. So this is what you see here in the Planck data points, and it's measured in a certain number of radii. So this typical separation turns out to be a few hundred parsecs. And it's definitely larger than the disk scale height, which typically already tells you that it is larger than what you have an effect of stellar feedback. If you think about, you only can drive large structures before basically radiation or whatever winds are basically blown out things. She also compared it to the Tumri length. So this is basically the shearing you kind of expect when you have a 2D disk that is stabilized by rotation. And here the length you expect from 3D turbulence injected in the medium. And it's mostly consistent with basically having 3D fragmentation due to turbulence. So this might point to the fact that large-scale motions play no role. However, I think there's more work needed, but this is the kind of analysis that can be done now. So to take away from this is basically the structure. The gas is very responsive to its external comedians. I think we have now in our hands the tools to better understand which processes are setting the molecular gas structure. And it's clear that these processes are acting on local scales rather than global galaxy properties. So the next, I'll talk about star formation. And for this, we basically asked a very simple question. We took a map of a molecular gas distribution of a star formation ray tracer, here H-alpha narrowband imaging, and then we asked which pixels or sidelines we only see the gas tracer, where do we see both, which are shown in pink, and which are the ones where we only see the star formation ray tracer. And then we basically said, okay, we are tracing the full star formation cycle from molecular gas to exposed star formation region, and how does that vary across galaxies. So that's work done by Xian Pan. And she did that for 49 galaxies at a common resolution of 150 parsecs. So what you see here is the typical fraction of the sidelines that have emission that have contained both tracers. So it's usually around 30%, and all the three bars are the same. So that means there is no trend with stellar mass. This changes dramatically if you look at the sidelines that have molecular gas emission only or star formation rate emission only. So basically means if you're going to very high mass galaxies, your sidelines will be dominated by sidelines that have molecular gas only, so non-star forming gas, at least given the tracer and sensitivity. And if you go to low mass galaxies, you will have a lot of sidelines where you see the H2 regions, but not any molecular gas. The other thing to question was now about this non-star forming fraction. Yes?
Could this be a fact that the gas overall is lower density for mass galaxies, so that it's not detectable in any way reflectable, or?
I think one way to understand that is probably indeed that if you go to low mass galaxies, your ISM is more atomic. So basically, the molecular gas is, yes, I think it's, yes, sorry. Yeah, so one effect is clearly that there is less molecular gas because you're more in an atomic gas-related regime. The other point is that the tracer used might be more compromised, though I think we checked for that mostly. And the other thing is that the overall gas surface density is lower. Also, it means that whatever energy you input, if you assume that the star forming regions are roughly similar, they are much more efficient in dissociating already their birth clouds. So about the star forming gas fraction, what you see here is there's no trend across the main sequence, but also not with galaxy type, which might tell you that whatever star formation happening, it's the same. The thing that was interesting, if you look at the CO only fraction, that they are early type galaxies, if they contain molecular gas, they seem to be that those are not totally star forming, and which is kind of also consistent with what the Wisdom project has been seeing. And this can be understood basically that molecular gas in those early type galaxies is stabilized against collapse and therefore star formation. One other aspect about the star forming gas fraction, you could also then just assume that you're timing the process by molecular gas plus star formation on star formation only. So the ratio where you see molecular gas over the time where you see the star formation happening, and tells you, if you take it together with the scaling of how long you expect star from H-alpha emission to be present, can tell you something about time. And the interesting thing here is, again, if you look at this as a function of scale, so basically what you see in the dark gray are the typical resolution that a lot of surveys like, I don't know, Heracles, SAMI, MANGER are achieving. And then what happens if you start to push to about 150 parsecs, so where you start to separate the process, you see basically that the trends are starting to decouple. And it becomes more obvious if you look at the more massive galaxies, that you first is that basically you need to resolve those trends. In order to see such trends, you need to resolve everything below 300 parsec. And the next thing is that the scale factor is about between 1 or 2.5, so there's a linear scale. So that star formation basically happens very quickly. And that's the lifetime of molecular clouds. So that is basically, if you say the time you see H alpha is 5-10 million years, which gives you a time. About the gas surface formation rate, surface density, and completion time, we try to cover a significant fraction of the optical disk, so that allows us to separate those in environments like the center, the bar, spiral arms, and the disk. And we can then ask, what are the typical values we measure in these different environments? And if you look at the molecular gas surface density and the star formation rate surface density, the one thing that stands out is that centers have higher densities, both in molecular gas as well as star formation rate. There's the remaining more disk environment. They are very similar, though there are some deviations. The thing that I found surprising is that this basically doesn't totally translate in a huge difference in the inferred depletion time, which is the ratio of the molecular gas surface density and the star formation rate. One thing that has been looked at a lot, especially in surveys with about half a kiloparsec resolution, or even globally, is how the three observables that are believed to describe very well the star formation rate and galaxy stellar mass, star formation rate, molecular gas mass relate. I already introduced you about the star forming main sequence, that is star formation rate versus stellar mass. You probably all have heard about the star formation rate versus molecular gas mass at the Kennicutt-Schmidt or Schmidt-Kennicutt relation. At least I hope Barry has told you everything about it. Yeah.
Just going back to the depletion time being so similar in these cases.
Yes.
Is that surprising, or is that expected from your simulations or other arguments, or what do you make of that?
It's not totally clear what to make of it. It might point to the fact that indeed once star formation gets started, it's just the same. In some sense, with higher gas surface densities, you expect higher faster depletion times. If you think extremes like ultraluminous galaxies, you expect those have significantly lower depletion times. And you kind of would have expected maybe the centers are already approaching such an extreme regime that it makes a difference or not.
Yeah.
And but this, we were not digging totally deep, but that is kind of a bit puzzling. I think also if you look at depletion times, I mean, you have the starbursts, and the starburst galaxies have lower depletion times if you move off the main sequence. So this maybe tells us that being within the normal population, the variations aren't that large. So coming back here to the, I was at the Kennicutt-Schmidt law, and then basically molecular gas mass versus stellar mass has been recently coined by Lin et al. As the molecular gas main sequence, has been studied years before. And so you can look at that. Since we have a resolution, Ismail Passer, a former PhD student at MPIA, he looked into a relation, and you kind of see that you still recover those relations at about 100 parsec. And the interpretation of these relations has been basically that with the stellar surface density, you're tracing the gravitational potential. So that is the hydrodynamic pressure, which is setting the molecular gas properties. And the molecular gas properties then determine how you define your star formation rate, so how efficient the gas is in forming stars, which basically explains why you have a relation between the stellar mass and the star formation rate. So based on this argument, you expect that you have the least scatter in this relation, a slightly more potentially scatter here, and then there's more here. So since we had 18 galaxies to play with, so you see the three different relations, and they are color-coded by the stellar mass of the objects and the number of star, how much they vary in their star formation rate gives the size of the symbol globally. So the first thing you notice, there are no trends with color or size among the three. The other you notice is that the scatter is differently large between the three, with being the smallest among galaxies for the Kennicutt-Schmidt relation. So the slopes here are the means of the individual slopes measured per galaxy, and here compared to the global slope, which can tell you what's happening. So basically, there's no trend in the global properties. The smallest scatter is in the star formation rate versus molecular gas. And our interpretation has been that this basically tells us the star formation process is basically determined by the properties of molecular gas, and it's the properties of molecular gas. It might be more parameters that are causing its variation than just the stellar potential.
Logarithmic slope?
I think so. It's the slopes in these. Yes, yeah. It's log.
You're saying the middle one has a slope of 1.
About, yes. I know, yes. No, I will not. We can talk this afternoon. I'm very happy to talk. There's a lot of ways how you measure and how you treat your observables, what you're getting and what you include. That is the short answer to this. And the long answer we can have this afternoon. So people have also looked in basically the 3D space, and there's been the argument that there is a plane that you can fit with this function. And the question was always, is that a single plane, or does it depend on galaxy properties? So we broke up our galaxies in their different environments, and you clearly see that there is a variation, particularly spiral arms in blue and bars in green seem to deviate from the global value or the disk value, and centers have a very large spread. So clearly there must be secondary parameters that are impacting the relation of these three parameters. So yeah, just to summarize, star formation efficiency varies, and also the process usually is very fast. So stellar feedback, just here's what I described. You have molecular cloud, it collapses, star formation sets on. During the onset of star formation, even in the protostellar phase, there are already winds that are starting to impact the surrounding molecular ISM at some point. These are strong enough to disrupt the cloud, and there's dispersion. So there are these pre-supernova feedback mechanisms that are winds, radiation, but also then there is supernovae that go off. And one big question from the simulation side, as I understand it, particularly that are larger, is to understand how important are these pre-supernovae impacts compared to supernovae. So one aspect is to try to understand this. So one way to do that is applying basically this uncertainty principle that Diederik Kreisner and collaborators have propagated. And for that, they basically look at a tracer of the cold gas and of the stars. And they look at the in different kind of apertures, and they basically use this ratio of the gas to stellar emission to basically determine these different types of information. There's a lot of information that can be gained. I'll just show one example, work done by Jeon Kim at the University of Heidelberg. And she used 50 galaxies and basically looked how this ratio varies. So you see that the typical cloud lifetime, which basically from 0 to here, is about a few 10 million years. The time there, the two traces overlap, is basically they expect feedback. So this is very short, typically below the 5 mega years you expect for supernovae to start to come in. The interesting part is that there is a trend in the lifetime that it is getting lower for lower mass galaxies. And this trend likely has a fact also to do with our tracer becoming more compromised at lower stellar masses, so that there's an impact. So there's some important things to do. However, so I think the jury is out if this trend indeed exists, but it's very clear that the lifetimes are short for all galaxies. I'll going to skip this. So also about feedback, I think JWST has handed us some tremendous information. So this is the Nearby Galaxy NGC 628 or a Phantom. galaxy. So you see there are a lot of these bubbles that were really striking in this galaxy, but others. And Liz Watkins, a postdoc at the University of Heidelberg, has gone out and measured all these bubbles. So she identified about 1,700 visual bubbles. And she could see that those are linked to the presence of spiral arms. And if you look at the downstream or upstream, there's a difference within the distribution. Their typical sizes are about 100-ish parsecs, so consistent with what people roughly think is the scale height of molecular gas in here. And also there are bubbles that are overlapping, and there's indeed, they tend to be overlapping, and bubbles potentially might be also merging because the size distribution is not fully consistent with what you expect from just having explosions. Just going after understanding better what's going on with this huge bubble, which is about 1 kiloparsec across, Ashley Barnes, who's an ESO fellow, has studied more into detail. So if you go from the center of a bubble and you move outwards, you basically, or white, you basically see that there are traces of FUV light peaks first, then you see a strong peak in dust emission that is at the rim of a wider CO distribution. And if you look at the distribution of the ages as a function of radius, you basically see that there is quite some peaks in star formation, very young at the edge of a bubble. And the idea is that potentially this expanding bubble was triggered originally by star formation and then is starting more star formation at its rims. And having more statistics and more than one example will be very interesting to understand how important these star formation caused bubbles are. I skipped over the first part because I wanted to have some time for some others, but basically it's becoming clear also from other work in the literature that pre-supernovae impacts are becoming important. The role of supernovae in shaping the ISM, I think, is less clear from the observational side, but I think JWST holds big key to understand what's going on. So the last science topic I want to cover are basically galaxy centers. And in this galaxy, the one thing that stands out is basically this blue box, which is the inner part. There is a stellar cluster, nuclear star cluster sitting inside. Its properties have been studied well with HST, and they were similar to what we know about the nuclear cluster in our Milky Way. So with JWST, the age could be determined very well to about 8 gigayears old. So this is work by Niels Hoyer, a PhD student at MPIA. And it is very clear that this star cluster is too old to cause this cavity in the gas and dust, where you basically see in orange the gas distribution. And it's very curious. Also, you see that there's a small offset of a mid-infrared emission, and it's not really clear what is causing this. So I think this highlights some of the potential insights that JWST data brings in addition to having HST studies. And the last I want to talk about is the central starburst of NGC 1365. It shows up very nicely in red in this JWST image. And Brad Whitmore has combined this with a previous study of HST data. And you see basically in red are all massive clusters of about 10 to the 6 solar masses and more that he's identified. And he now has a sample of 37. So basically JWST has about doubled the number of embedded massive star clusters. And this is also the galaxy with the most massive star clusters within 20 megaparsecs. So this is a very unique environment. And this basically motivated me to understand what is causing that. So what you see here is basically the gas stream along the stellar bar that is sitting there and that is feeding in a sketch roughly the inner starburst ring. And if we go from here, basically this is molecular gas distribution obtained with ALMA at the same resolution as the JWST data, so about 30 parsecs. And if you have a careful look at the kinematics, so now you're seeing basically This is the declination, this is roughly RA, and this is velocity structure. You see in the inner part, there's a dynamically cold, smooth, rotating disk, and out here, these parts, you have a lot of complex bar-induced streaming motions, even with multiple peaks. The individual decomposition of the gas gives you typical gas densities in line dips, similar to what we observe in the Milky Way central molecular gas zone. It's very interesting to see where the star formation is happening. So what you see here is a 10-micron image, and also overlaid are the clusters detected by Brett, plus some others identified at 10 micron. So you see the star formation is happening along there. There's a lot of these the streaming motions and the complex, but inside in the inner disk, there's basically no star formation. So this could be speculative, similar to what we see in early type galaxies. And if we look at this compared to Ramsey simulations, so this is about the snapshot that we think best represents the gas distribution as well as the location of these young clusters. You see, even if you only go 20 years back in time or a few mega years ahead in time, the distribution of the gas changes rapidly. And the reason for that is that this galaxy has a very long, strong bar and a very high inflow fraction. And that depending on the timing, this geometry could change very quickly. And that basically brings me to just some more advertisements. So I told you there are these 4 very large programs going on. We have released data products for these 90 galaxies in CO. The imaging of the galaxies from HST are available via MAST. Also, the Muse data products are available. All JWST data is public immediately, as this is a treasury program. In addition, there are catalogs. There are also combined catalogs of some of the products that are available. If you're interested more in different science, please visit our website. I think there are now more than 80 papers on all the variety of topics. We also have a lot about molecular gas and chemistry, but also other topics. Also, I would like to advertise likely next week, our AppJ focus issue on the first set of science that can be done with the first 4 galaxies is coming out. Also, Janice Lee will be here in 2 weeks and will give you a colloquium. And I'll promise you she'll not talk about the same things, but you should remember everything you learned about PHANGS and also at Caltech. I want to finish just with some other images from JWST. So this is JWST together with AstroSat UV emission in blue. This is the 200 micron versus PA emission. I think this is stellar light versus the 3.3 PA emission. So just to give you an impression of the many information that probably can be gained, and we have only started to scratch our deer. This is one other project I'd like to advertise. It's led by Enrico Congiu. You might remember, know him. So this is a 100 pointing mosaic of NGC 253. And this is covering the full optical depth and disk, sorry. Resolution is about a few 10 parsecs. And just to give you information, the data was just taken. And also that is something that will become public. And so this leads me basically to the end of my presentation. So I hope to convince you that understanding star formation or studying the star formation process on cloud scales has become now much more exciting, because we have now way more better statistics. We hope that the PHANGS sample is be widely used also by the community as a benchmark for normal galaxies comparison to other aspects or other parts you want to use it. I think the thing to take away is that molecular gas is close to energy equipartition. It means it can react quickly to changes in its local environment. I think There's still a debate what's going on, what is setting its structure, the filamentary structure we see now at these scales of galaxies, and how that filamentary structure connects to the filaments that people studying the Milky Way are very excited about. Star formation is clumpy and overall it's inefficient. Not every molecular gas we see is starting to form stars. However, when it starts, it proceeds very fast. And I think the amount, which feedback or relative role of pre-supernova feedback and supernova feedback is still unclear. I think adding more information statistics will be important. I also would like to thank all the staff of all the observatories who have helped us to support and prepare and get these data sets in hand. Also, I would like to thank Carnegie for hosting our team meeting in 2 weeks from now. Thank you very much.
Great. Thank you for the nice talk. It was a good way to kick off PHANGS month, I guess.
Thank you very much. It was very interesting. You wanted to ask about the star formation rate tracer with the age alpha.
Mhm.
How much do you think the result will change if you will use PHANGS alpha, for example? So something which is less affected by dust obscuration?
It'll depend on the data set used. So for MUSE, basically we have H alpha and H beta. So you can start to do the correct extinction correction. And that is working extremely well. The MUSE data is very sensitive. If we only have use H alpha from narrowband imaging, it will have an impact, particularly if we do in certain areas. Overall, the star formation process and the clearing time, I didn't go too much into this, and I didn't show that result, but so there's also a paper by Jaeyoung Kim where she did exactly the same analysis, but instead of using a narrowband ground-based H alpha, she's been using the 21 micron, so hot dust, which should give you basically, should be similar to PHANGS alpha because it gives you an access to the embedded phase. And there she finds basically that the overlap where you only see the embedded phase is only 1 to 2 million years. So given that, the impact on global big statistics shouldn't be too hard if you are interested in understanding individual regions, particularly where you have high gas surface densities, there should be changes. But the clearing time scale is very rapid, so in that sense.
Do BARYON.
I apologize if I missed it, but did you include neutral hydrogen maps?
We do include it for some calculations when we compare on kiloparsec scales. But on average, if we look at high resolution, we ignore neutral hydrogen because the typical resolution you can achieve with a VLA with sufficient sensitivity is a few hundred parsec, half a kiloparsec resolution, which is much lower. And even with the Meerkat array, you're still not at the same resolution. I mean, there's this extra large program at the VLA that Adam Leroy is leading, where they are pushing down below to a few 10 parsec resolution in Andromeda, the Triangulum galaxy, and I think 3 more dwarf galaxies, where you basically have molecular, the atomic gas at a cloud scale resolution.
Do you think
And
it'll change any of your broad conclusions?
The biggest question, I think not of a broad conclusion, the biggest question is always the transition from atomic to molecular gas. That is an important one, and to understand where it's happening, we are basically currently forced to work where we see molecular gas. And I think, and also the impact of the pressure of the measurements could potentially change more because at the moment, this is basically assumed that the atomic layer is homogeneously distributed. So there could be some more things. Also I think Eve Ostreicher keeps telling us we need to have the atomic component among the other theorists in the team in order to get the full picture. So I think, yeah.
Thank you. I have a question about the lack of gas in the central regions of some galaxies. So especially in when you showed us the gallery at the beginning, there are some that were very clearly had holes at the centers, and towards the end you mentioned that that can happen through interactions with the bar, but
yes.
This is kind of also time dependent. And so I was just wondering, since you do have a number of examples with these kind of holes at the center, does the diffraction tell you anything about the physical kind of picture underneath?
So this hole is really big. This is a few kiloparsecs across. The others, I think some of these galaxies, they are more a few hundred parsecs. I think those are probably dynamically related to resonances, how gas moves around. Having no gas at the very center, or much less gas at the very center, I don't have the numbers. Sophia Stuber, as part of her master thesis, did a classification of the CO morphology, and she has also looked in how many have these nuclear rings, but I forgot the numbers. I think about half of the barred galaxies have nuclear rings or so. And be aware, these are all star-forming galaxies, so they should be gas-rich.
Right.
So you should have that information. Also, there are some early type galaxies or more early type galaxies in here, and trying to spot some of them. Yeah, I think this is a clear example. Those usually stand out because they have more smooth gas disks, and there was a really nice paper by Tim Davies last year where he basically studied how the gas morphology changes as a function of galaxy type, or he approximated that by stellar gas surface density.
Thanks.
Any more questions? Oh, here you go. Yeah.
So you mentioned this, one of the mass trends might be complicated by the CO dark gas. So first, just to make sure I understand what that is. So is that gas where the CO is self-shielded and the H2 is not, or the other way around rather? What is the CO dark gas?
So CO dark gas is basically, I think if you look at the review by Alberto Volato, the idea is basically that because of the lower metallicity, the shielding of the molecules are different. So you start to dissociate the CO already much earlier because the dust are different when you have the H2. So you can still have the H2 because it can still self-shield.
Yeah.
There's the CO is already destroyed. So your molecular component might be as large as it is in a more higher metallicity galaxy. That's the idea. I think now with JWST, if the assumption is the PAH emission is working very well, would be perfect to test this. But basically getting at the molecular gas component in lower mass galaxies, less metallicity is hard observationally. And I know ALMA spent hours and hours to come up with ways to probe it, because even the continuum is hard.
Yeah.
I wouldn't call it X factor. Yes, but the X factor is another way to express that your tracer molecule has a dependence on metallicity, but it also depends on density and temperature of your gas. So it captures more.
Great. Let's thank Eva one more time.